Alrighty, welcome back to Rational Functions. Today we are going to look at horizontal asymptotes and points of discontinuity. These are the last things we're going to look at before we're able to graph all rational functions. It's all part of our analysis of these functions, so just determining what properties they have, what's going on with those things. We're going to start with the points of discontinuity, and it's based on the fact that this statement right here is almost always true. X plus 3 times x minus 1 divided by x minus 1. Well, we can do some cancellation of factors. So it's just x plus 3 equals x plus 3. Wow, this works for everything, right? Wrong. This does not work in one instance. It just doesn't work when x is 1. And that's because having this expression on the denominator causes a non-permissible value. It is not permissible for x to actually equal 1. When we graph y equals this side, it's going to look just like the graph of y equals this side. They're going to be almost identical, except when x is 1. At that point, we'll have a hole, a point of discontinuity to use formal speak. So where y equals x plus 3 looks straight up like this, if we introduce that non-permissible value, x plus 3 times x minus 1 divided by x minus 1, where those things could be canceled, we have this hole. It is an infinitely small little piece. It just says that this gets infinitely close to this point. It gets infinitely close to this point, but never quite reaches that exact value in there. So we represent that with this open or hollow circle, hollow point, to say we get infinitely close there, but never quite actually touch it. So there's a hole. But otherwise, it looks just like this other one. How do we find the coordinates of that point? In this one, yeah, sure, we can see it's equal to the point 1, 4. But how do we actually get that algebraically? We can see because we have the graph. What if we don't have the graph? Well, the x value we got from the non-permissible. And it's not permissible for x to be 1 because of this. Okay. So x is 1. What is y? Well, if you try to plug it in here, we get, I don't know, we get 4 times 0 divided by 0. Whoa, you can't just divide by 0. Everything's scary. But what we can do is look at the reduced form of the function. So once it's simplified, once that, how you say, point of discontinuity is dealt with, then we're just looking at this. And when x is 1, y is 1 plus 3. And then y is just straight up 4, hence the point 1, 4. So that's what we're looking at. That's how we're going to play with this for this particular game. We're going to see if there's something that can be simplified, and if so, we'll simplify it, and we'll figure out what value it should have had. Cool beans? The coolest of beans. So let's determine the points of discontinuity for each of these rational functions. We got 3 whole examples. I think that's it. And then we're going to talk about something else. None of these things are factored. So you're going to have to factor them. We need to figure out what x value throws this whole thing off and go from there. So f of x is all this jazz. We can factor it into something that what do I do with my life? That. And this simplifies. So if f of x is 2x plus 1 times x minus 4 divided by x minus 4 divided by x minus 2, well, then the x minus 4's can cancel, And we're saying it's the same as this as long as x is not 4. As long as x isn't 4, those are the same. So we have discontinuity. When x is equal to 4. Well, what's the y value? As x gets closer and closer to 4, f of x gets closer and closer to this. It's just like 2x plus 1 over x minus 2. It's going to behave just like that function. So 2x plus 1 over x minus 2. And that's equal to, how do you spell 9? Not a straight line. Oh wait, that's not 9 over 2, Captain Genius. Oh, I factored it like a doofus. X plus 2. There we go. Anyways, 9 over 6, which is 3 over 2. So as x approaches 4, f of x gets really close to 3 over 2. That's the point of discontinuity. I'm still on the right color here. So we have a point of discontinuity, or a hole, when x is 4. And when x is 4, y is 3 halves. Try the next ones. See what happens. As per usual, I'm just going to keep going. You can feel free to pause this video as is necessary. Boop. I'm going bigger. Okay. Because there's a common x minus 3 on the top and the bottom, we can reduce this and say it's basically the same as this line that I'm writing on now, as long as x isn't actually 3. So as long as x isn't 3, then yeah, they're the same. Therefore, we have discontinuity when x is equal to 3. Well, what's the y value? We'll sub it into the simplified form, because as x is getting closer to 3, g of x generally behaves like x times x minus 4 over x plus 2. Oops, it's not equal to that. It gets closer to that, which is negative 3 over 5. So our point of discontinuity happens when x is 3 and y is negative 3/5. Final example. Lots of square. So these are the same, but we got rid of 2x plus 3. which means that x can't actually be negative 3/2. Well, when x is that, what's y? It approaches 2x plus 3 over 2x minus 3. Which is something. 0 over negative 6. Well, that's 0. Ah, cute. So we have a point of discontinuity. Right there. Questions, comments, concerns? Haha, good joke. Haven't told that one all topic. Actually, I haven't told that one all topic. Wow. What restraint. That's points of discontinuity. There's one other aspect we have to address here for graphing rational functions. We know how to get vertical asymptotes. They happen when you have more of a critical value in the denominator than in the numerator. But horizontal asymptotes, for those, we're asking how the function behaves at its extremes. So, at the extreme values of x, of its domain. So as x goes to positive infinity or x goes to negative infinity, what happens to this thing? When you have a function, let's just, I don't know, x squared plus x to the 4 minus 3x cubed, and I don't know what happens here, 5x to the 3 plus 1. As x gets larger and larger and larger, these lower exponents start to matter less and less. This has an x to the 0. So on the top, only this will be really weighing on things. And on the bottom, only this will be really weighing on things. The rest can essentially be disregarded. There is a very formal process that we could go through, but for our purposes, it's less necessary. And we can just say we're going to look at the highest degree term on the top and the highest degree term on the bottom. And from that, we can draw conclusions. How do you erase things? Like this? You go like this? Bam, bam. If the degree of the numerator, if your highest degree term has a bigger exponent than your highest degree term on the bottom, then we're not going to have a horizontal asymptote. If the degree of your numerator, if that highest exponent you see in the top is lower than the highest exponent you see on the bottom, you will have a horizontal asymptote. But where? Well, that's the case where if you have, say, like 1 over x, or even x over x cubed plus 1. Like, what's going to happen? This is going to be huge. And when you divide by something that's massive and massive, it gets closer and closer to 0. Oh, my Zs. So that's where asymptote will be. But, say you have a case like, I don't know, 4x cubed plus x squared over, it's so difficult. X cubed minus x minus 1. Again, we're saying only that highest degree term matters. And everything else is like it's not there. And if we say that your coefficient of your highest degree term in the numerator is A, and your leading coefficient in the denominator is B, well then you could say you do have a horizontal asymptote at A over B, whatever that ratio is. So those are the three scenarios you could deal with. Based on that, determine the equation of the horizontal asymptote for each of these four functions. If it exists. If it doesn't, then you'd probably write something like it doesn't, or there's no horizontal asymptote. Well, here I go. I look at this one. I look at this term. I look at this term. I have a higher degree in the top than I do in the bottom. Therefore, there's no horizontal asymptote. Done. Next one. There's your highest degree term in the top. Here's your highest degree term in the bottom. They are same. They both have a degree of 3. So I'm looking at 6x cubed over 2x cubed, which is 6 over 2, which is 3. So I can say that this does have a horizontal asymptote. When where y is 3. Blah. Looking at this, looking at that, you can say, you don't have to say this, but you can say that you're looking at 12x squared over x cubed, which is kind of just like 12 over x. But that means that as x gets massive, this whole expression gets closer and closer to 0. We had a higher degree in the bottom, if you want to use the rules that are stated at the top of the page. But essentially, you just need to make sure you can determine that the horizontal asymptote is where y is 0. And then this last one, yowza, this is in factored form. Woo-wee! How do we do this? Well, I'm going to take this piece, and that's a huge highlighter. Can I shrink this down, please? Thank you. I'm going to take this piece. I'm going to take this piece. I'm going to take this piece to that power. I'm going to take this piece. I'm going to take this piece. I'm going to take this piece to that power. Because that's the highest degree term in each of one of those factors. So when I look at this thing, what I'm really looking at is 2x times negative x times 3x squared on the top. I don't need those constant terms. They're irrelevant as we go towards infinity. And on the bottom, we've got x and we've got 3x and we've got x squared. Don't worry about those constant parts, because again, they're irrelevant as we approach infinity. So on the top, this whole thing is like negative 6x to the 4. On the bottom, we've got 3x to the 4. Did I even do that right? No, I didn't. That's not even 3 on the top. You know what I forgot to do? Watch out. I didn't square this 3. So actually, this is like 18. Again, just in case you missed what I screwed up on, this 3 is squared. Doy. And when this reduces, this is basically negative 18 over 3. So I can say that there's a horizontal asymptote where y is -6. Those are the last two features we'll need in order to be able to graph rational functions. Do make sure you are comfortable finding those. So make sure you can find points of discontinuity. Make sure you can find the horizontal asymptotes. I would try practicing these things. Question 4 in that text for that page range, you don't have to worry about graphing it yet. If you want to try it. Feel free. I'm pretty sure I assign it again. To be honest, I'm not actually certain. Yeah, I do. Just looking ahead. I definitely reassign question 4 so that you actually have a chance to graph it. Give this a go. Do whatever you can in terms of how much time you have. If you have questions, please do contact me. Let me know as per usual. And may the force be with you. Always.